The title of your lectures again, just so I
Just yeah, it's changed. Yeah, in the end, I'll talk about something else. But that's like 3 days from now. Yeah. Yeah.
Now, if we have to move like
go ahead and get started.
That's good. Yeah.
Normally for talks I wait 5 minutes, but for the school it's like, you know, everything kind of runs
Yeah.
most of the time.
like how do we chat like
Okay, so let's get started with the second lecture for today. So before I introduce the next speaker, just a very quick announcement that the schedule this week towards the end of the week, particularly on Friday, is slightly different than what you would have received in your packets, or and probably even different from what's posted up here. So as always, just consult the Boulder Summer School website for the most up-to-date schedule. So on Friday, there are going to be 2 research seminars that Vedika Kamani is going to be giving in addition to the scheduled lecture. So consult the web. Okay, so just to introduce now our second lecture for the week. It's a great pleasure to have Liang Jiang from University of Chicago is going to be talking about bosonic error correction.
Okay. Yeah. Hello, everyone. I assume the audio is working well. So, yeah, it's good. Yeah. Okay. Well, first, it's a great pleasure to come back to the Boulder Summer School, because I was organizing a similar one like about 5 years ago about the quantum error correction and quantum information processing. And I think the field has a lot of development. And I think it's also have a good connection to like dynamical controlled open quantum systems. And I think it'll be a good topic, like also relevant to a broader beyond the quantum information audience to talk about the quantum control, quantum error corrections. And so I think you already, Victor already introduced some of the basics for quantum error correction. And so in my lecture, I will try to maybe talk a bit more about a particular application for quantum error correction for bosonic systems. And but I would say like maybe the implication is probably a bit even broader. Is I hope that the takeaway message is not just we can use it for bosonic error correction. We actually can use error correction for many different physical platforms, and also hopefully can also use for different applications beyond the computation and the communication. Okay, so maybe let me just let's start. Bosonic quantum error correction, but first as a general motivation. Is I would put it as a co-designed quantum error correction. So if we look at books, when we talk about the standard correction, for example, you open the books like by Nielsen, Chuang, and so on, they typically will think about the error correction works considered for quantum bits, which have its bit, yeah, even larger. Okay. The qubit's getting smaller, so we should make it bigger. Yes. Okay, thanks. Okay, all right. We think about the qubits, and but it's a nice theoretical model to think about just 2-level systems, and you can see the bit flip dephasing and depolarization errors, or sometimes even erasure errors. But in practice, our physical systems are not just the qubits. Right? We have our even superconducting qubits. It's actually a harmonic oscillator with multiple levels. And for like a system, also other levels it might lead to. So it's a good theoretical model, but practically, it's actually something different. And also for most of the error correction tasks, it's mostly for computational tasks. Do like a factoring or like other like quantum algorithms. But in practice, we know like we have many other applications besides just the computation. We can use quantum systems for communication, sensing, simulation, or even like other like a non-trivial demonstration of quantum advantage. So it'll be good to think about broadly, can we use error correction for other applications as well, rather than just for computation? Then in this context, you might find that maybe one need to design error correcting codes slightly differently. For example, if you want to do sensing, you probably want to make sure when you correct the noise, but don't erase the signal, which is different from error correction. Okay, so that actually motivates us to think about a co-designed quantum error correction. So exactly, that's what I'm going to explain. So it's kind of a word that you may see lots of the proposals that people put co-design in there. And my understanding is the following, because quantum error correction can think that we have a physical hardware, and we also have application. Okay, we want to use our physical systems to solve some practical relevant problems. However, there's a gap, and the gap is actually there are some decoherence and imperfections of physical system. And also, in order to implement some of the quantum circuits, we do worry about the connectivity and scalability. And here, I want to put the quantum error correction in here, which connects the application and it connects the hardware. More specifically, we need to think about, rather than just the abstract qubit, we need to think about the physical platform. So what is the dominant error in your physical platform that you need to correct, which may be different? Some of the platforms suffer more dephasing errors. Some of the platforms suffer excitation loss errors. Those are different errors, and you can design different error correcting codes to correct them. Okay, so, and also for example, you need to think about dominant error. And also when you do error correction, you need to think about what are the available operations that is easy to implement with your physical platform. Not all operations are equal. Some of the gates are easier, some of the gates are harder. And you want to find those ones which are natural to the system. And sometimes you may even consider doing some like autonomous error correction if your system have an efficient way to cool down, but without erasing the information. And also sometimes you need to also worry about the connectivity. Do you want to prefer to have a two-dimensional connectivity, or you want to have like a long range, like a distributed quantum computing over a network? So all those things should be taken into account when you design quantum error correction schemes. Okay, and the other aspect is correspond to just the computation. One should also think about applications. Are you consider doing computation or do communication? Or you are thinking about quantum sensing or other applications. And for these different applications, you need to design like a error correcting codes, hopefully will be most efficient. For example, when you do communication, you want to design the code which can maximize the communication rate. Similar to our classical communication, we now use 5G based on polar code and the LDPC code, which approach the quantum channel capacity that was predicted by Shannon about more than half a century ago. But now when we design quantum codes for communication, we may want to also focus on some of the potential advantages to improve this aspect for communication. And when you do sensing, you also want to maximize your sensitivity while doing error correction if needed. So this is just about the general aspect of code design, which my simple version is you need to think about the hardware, you need to think about the application, which usually this is where the physicists we take care of. And for applications, maybe you may want to talk to computer scientists or some people who work on all kinds of applications. So, but it will be good to think about the holistically how we actually design a robust quantum system that can connect the hardware and the application. Okay, so now as for our topic of bosonic error correction, I also need to maybe give a bit motivation about the importance of bosonic quantum information processing. So we actually use bosonic systems a lot for our quantum information processing, even though sometimes we call it a qubit. For example, when we use the Transmon qubit, it is actually a harmonic oscillator. And if you drive the system harder or if the nonlinearity is smaller, it's actually effectively like a harmonic oscillator. And there are also recent investigations on error correction. It's based on superconducting cavity modes that with the higher levels of redundancy to correct errors so that you can store information longer. And for communication, it's natural because our fiber networks, our modes that send over fiber are actually wave packets, which are bosonic modes. And for sensing, for example, the gravitational wave detection, the LIGO, it is an interferometer, which is based on optical modes. And for simulations, there are those Bose-Hubbard models and the cold atom systems. And even for the boson sampling, quantum advantage experiment is actually based on bosonic modes. So for many applications, we actually do use bosonic modes for information processing. Okay, so there are different applications. And also at the same time, there are also different physical platforms. So we're probably all familiar with optics. It's a bosonic modes. Microwave, it's a bosonic mode. And if you can think of more, maybe can we add more to this list of bosonic modes? Just speak up if you can think of more. Yeah. Louder, please. Yeah. Free space communication, that's this like optical or microwave modes, right? So are there other modes which are bosons, we call it? Molecular vibrations, which is vibrations, or sometimes those are the phonon modes, which are bosonic modes, right? Oscillators, like a mechanical oscillator, the phonon modes, which is actually an important platform because the advantage of the phononic mode is the wavelength, the speed of sound is much slower. So that with the same length, it actually you can build a much smaller device to make it more compact, right? So what are the bosonic systems? Good. So magnons are kind of spin wave excitations, which give you like a collective spin wave excitation, which once you have so many spin waves, you make those Hausten-Primakov approximation. So it becomes effectively like a boson, right? And are there more? Right. Yeah. That's true. And also depend on the modes that you may have a selectivity of the modes that, for example, you just address the Kittel mode for the magnon if you have a uniform field that's coupled to the magnetic field. Yeah. Which actually recently in Yasu Nakamura's group, they actually generate using superconducting system to generate single magnon modes. And you can process information with magnon modes as well. Yes, there's another thought. Yeah. Cooper pairs. Yeah, that's, yeah. Yeah, because once it becomes bosonized, you can do it. Yeah, Victor? Yeah, yeah, it's not quite a harmonic oscillator, but I would like to put it here because it's indeed indicating that there are like many levels in the system, which is similar to the bosonic modes. Yeah. Yeah. Yes. Exactly. So like sometimes a cold atom cloud, which you can generate like a spin wave excitations, right? So it's like an atom ensemble, atomic ensemble. Okay, maybe I'll just write it here. Okay, so there are actually a lot more. And the purpose I want to list here is that once you're under a correct regime, there are many systems that we can model it with bosons. And the reason we're interested in this is because actually for quantum systems, there are only limited models we know how to solve exactly. Two-level systems, harmonic oscillators, and hydrogen atom, right? So those are just like a few good models we know how to model it really nicely. And also for these bosonic systems, it has its unique features that we can use it for error correction. Okay, so maybe let me just give a comparison between like a typical like bosonic systems and the qubits. Okay, so now the essence of quantum error correction. So here, I hope you just remember one of the keywords, which is redundancy. Doesn't matter whether you do classical or quantum error correction, the only thing you're using is redundancy. You introduce redundancy to kind of separate between different logical states, so that if error happens, you will not mix different logical states. That actually works for both classical and quantum. But for quantum, besides don't mixing different logical states, you want to also make sure that you don't change the likelihood of different logical states when environment gets some information from the system. Okay, so maybe now let's look at different systems for qubits. If we only have a two-level system encoding a qubit, there is no more redundancy we can use for error correction. So in order to overcome it, we need to put more two-level systems. So that will give us a 2 to the n dimensional Hilbert space, maybe to encode a two-level logical space. So here, typically, what we do is to do a tensor product of qubits. Now for oscillators, or sometimes we also call the bosonic systems. So even with a single harmonic oscillator, we already have many energy levels. So in principle, we already have the redundancy to encode just say two-level system using a harmonic oscillator. And that redundancy, in some sense, already kind of imply we can probably do some error correction schemes that help us to suppress errors. So many levels in single oscillator. So now when we design error correcting codes, we not only need to know the system, we also need to know the error models. Or the practically relevant dominant errors. So maybe I should make a disclaimer at the beginning, is that the goal of error correction is not to correct all errors, because there's no way you can do it. Because if you do that, you will correct all the logical operations and so on. The goal of error correction is to correct the dominant errors that practically you want to like suppress, so that the errors will be suppressed to higher order. So when the system gets larger, the errors will become high order and become negligible for the particular computation task or other applications you want to do. Okay, so the goal is not to correct all errors, but we want to correct some relevant errors. So for qubit systems, the typical errors, I'll write an error set, is a subset of individual qubit errors. And if you have n qubits, it's basically a tensor product of these different parties. And here I made the assumption that it's only just a bit flip dephasing or depolarization error. And in principle, you can also include, say, the two-level system had the third level. So if the two-level system go to a third level, it becomes a leakage error. But here, I just say, okay, suppose we restrict ourselves to two-level system. This is sort of the largest set of errors you can consider. And the errors you can correct is a subset of that error. Okay, now for harmonic oscillators, actually the errors are, so this is typically called the Pauli errors. While for harmonic oscillator, the typical errors actually are the excitation loss and the dephasing. So for example, if you have a photon loss annihilation operator acting on an n-level system, you will get a bosonic enhancement of square root of n, and it reduces the excitation number by 1. And this error has a feature because you're not going to eliminate all the excitations all at once. You reduce the excitation one by one. And if your initial excitation is even, then you reduce the excitation by 1. It can change the parity from even to odd or from odd to even. Okay, so there is some structure of these errors in the bosonic system when you model it as excitation loss error. And there are also other errors, which is A dagger A. I'll probably drop the daggers for convenience. And it will also have a feature, which is the excitation number don't change, but there is a proportionality factor, which is proportional related to the bosonic enhancement. So notice that all these errors for both loss and dephasing, at least the excitation number do not change dramatically. And that is the feature that we will use for our error correcting codes to correct bosonic loss errors. Okay, and so that's actually related to the code design, that if we know the feature of the error, we can design the codes more efficiently to correct these dominant errors. Okay, yes, Leo.
You haven't mentioned the qubit, bosonic qubit, so it's not necessarily 2 levels here. It could be something much more complicated.
Yes, it could be something more complicated, and I'll give you 2 examples today, and tomorrow I'll give you a 3rd example. Yeah, but here there's another feature which is less obvious for these operators, is actually what happened in the phase space. So maybe just before I get to that, may I know like how many people have a familiar, at least learned from your quantum mechanics about the Wigner function? If you haven't, if you have, raise your hand so that I'll get an idea. Okay, I think probably like, okay, maybe 80 or 90% people have learned about it. So the Wigner function, you can think it is just a quasi-probability distribution of bosonic modes. So suppose you have a harmonic oscillator, you need to talk about the position and the momentum. So the Wigner function would have this position momentum with some quasi-probability distribution. Okay, suppose you have some like quantum states localized in some region in the Wigner function. Then when you apply these errors to the Wigner function, you'll find that it will just smear out the Wigner function a little bit in the neighborhood. It will not move a coherent state from here to somewhere else. There is some locality in the phase space of these errors, which is important because, for example, I can encode, say, logical 0 here, logical 1 there. Then if I have an error, it's unlikely it will go all across the phase space to the other side. And that actually will be important in our later discussion about bias preserving error correction. So there is, besides the photon number, kind of a slow change of photon number, there's also a locality in phase space. And this is also important when we design error correcting codes, so that you can imagine you don't want the logical state to be mixed. You may want to design them to be separated in your phase space. Okay, so now I think that's basically I want to talk about the essence of the error correction is redundancy. And fortunately, we do have a lot of redundancy in our bosonic systems. And I'm mostly talking about a single mode error correcting codes using bosonic modes. Yeah. Yeah.
For all this bosonic thing, like for oscillator, like a position
Okay, good. Yeah, so the question is like, am I oversimplified just to say this is the dominant errors for the practical bosonic systems? So I would say like, maybe let me just give a few practical relevant error models. So let me just write it to here. So one of the common error model is called the excitation loss error, which you can think that the photon going through a fiber and gets absorbed, or goes through beam splitter, partly gets reflected. And this is a dominant error which in just a few minutes, I'll write down what's the cross operators, the most general quantum process for the loss error, which is in terms of powers of annihilation operators. Okay, you can think there's a probability no photon loss, probability 1 photon, 2 photon, and so on. If the loss is small, then probably mostly will be no loss or small loss. And they are also dephasing. And for dephasing error, it kind of corresponds to if you have a optical modes, somehow there's a path length fluctuations. And if you have a superconducting cavity modes, then probably there's some other level systems that's jumping around, induce a random phase shift. And those are the dephasing error. And you can write it as powers of A dagger A. And then I think the model error you're referring to is more like kind of like some thermal noise. So suppose the system gets kind of like heated up or induce some like a random displacement in position and momentum. So then basically what happened is that you can think it as the system undergoing some displacement operation on your state, and you integrate over some probability of alpha, d square alpha. Now notice that the displacement operator for small alpha, you can expand it as A plus A daggers. Okay, so notice that this will consist of A and A daggers, or some linear combinations, while the loss is mostly A, and the dephasing is A dagger A. Okay, and later we'll see like we're mostly focusing on the loss error. The reason is because for optical system, it's mostly loss. And for microwave systems, if you cool the system down really efficiently, it will be mostly loss as well. But there could be heat. And actually, some of the error correcting codes I talk about can correct both loss and heating. And you will see with the error correction condition, if you remember, you have error EI and EJ, and the EI dagger EJ, if EI is A, EJ is A, it becomes A dagger A. So if you can correct some of the loss and heating errors, those codes can also correct some of the dephasing errors as well. Yes?
Comment on, like, seems like maybe it's a character or distinction between Bosonic codes versus qubits. That like here the errors that you're listing primarily are, well, all the ones you've listed are somehow incoherent and very different flavor than the ones Victor talked about. Phase error or bit flip.
Bit flip, yeah.
So is the distinction that I'm noticing with Bosonic versus qubit?
So there is a distinction for Bosonic. One thing is that, for example, I mentioned that the superconducting qubit, Transmon, is an aharmonic oscillator, right? And so what happened is, for example, we look at the Transmon. So we have a ground excited and the second excited states. You could write it as a 0, 1, 2. The issue is that the energy difference between the first excited state and ground and the second and the first excited state, they are sufficiently different so that when you lose a photon, the environment knows what's the frequency of the photon, and the environment knows which level, which particular Fock states the system is projected to. However, if I have really a true harmonic oscillator, then the level spacing are exactly the same, then that error, even if the environment gets a photon, the environment still don't know which particular Fock state it's in. It will still be in some superposition or mixture of different Fock states, while here, actually, if you lose the excitation, you know what it is. So therefore, we actually do not model the Transmon as a bosonic modes unless the photon loss rate is much larger than this like energy level spacing differences. Okay, so that's why actually for Transmon superconducting qubits, we model it as a 2-level or few level system. But once it can couple to a superconducting cavity modes, which is a bosonic modes that we can have. Yeah, so there is a subtle difference, but it's really need to think about the physics, about how the noise, whether or not, how much it differentiates the different levels of the system. Yeah. Yes? How large is N? So there are experimental demonstrations of the qubit codes. N is range from 0 to 4. And there are also GKP states, which N goes to 10 or 20. Okay, so you can have like average 10 photon encoding for GKP. Yes, well, it depends on how good the dephasing is. And if we look at the superconducting systems, actually the reason they got the dephasing for superconducting cavity is because it coupled to some environment which actually just go up and down randomly. But if you suppress that, you can also make sure the cavity is basically T1 limited by decay. Yeah, but it is something that one should be careful. If you have a large photon number, the dephasing error sort of because of this factor, it could become more and more relevant. Yeah. Yes.
More on the locality in phase space. Is it because
Yeah.
the operators connecting them are very long?
Yeah.
Long string?
Okay, so the locality in phase space, you can think it this way, that this A, let's think this, suppose you have like a small, like a e to the I, small epsilon A dagger A, okay? So most, as you can do Taylor expansion, it'll be identity plus I epsilon A dagger A, and so on, right? So the identity says the state stays there. And this quantity, you can think it as this operator, we know what it is. It's just some like a phase rotation in phase space. So it just rotated a little bit of the original state. So that's the contribution of this quantity. So basically it just only slightly shifts the phase space a little bit. But if you want to go more rigorously, is that any operation of quantum states, you can write it as some like a superposition of displacements acting on your system. Okay, then that superposition of displacements will tell you what is the typical distribution of how far you are moving away from your system. And from any states that we write in here, you will see it's actually pretty local. Yeah. All right. Yes. Oh, so here the dephasing, I think generally, if you have a bosonic mode, like it's a cavity, suppose you have an optical cavity, the length can fluctuate, and that causes the dephasing. So here is just a purely like a model for the bosonic system. It could be induced if the system coupled to some two-level system that kind of randomly jump up and down, that shifts the length of the cavity. Yeah. Okay. Yeah. All right. Yeah. Yeah. So, okay, if you can stay for another 5 minutes, we can come back to that question because it will be more explicitly clear about what's the code that we're considering. Okay, so the short answer to your question is we can consider alpha equal to 2, well, alpha equal to square root of 2 coherent states with average 2 photon number. And that actually allows you to create a superposition of coherent states that allow you to do error correction that's correcting single photon loss error. But if you can stay for another 10 minutes, we'll actually get to that bosonic error correcting codes. Okay, yeah. All right, so, okay, let's move on to the, I hope that we'll be able to get to, before we get to actually more on the error correcting codes, just to give make sure everybody is on the same page, some background of bosonic systems. So the first background, I would say, is just think about a simple harmonic oscillator, but in the classical picture, because that actually gives us a very good intuition. So spring, mass, displacement. And so classically, we'll write the position as amplitude cosine omega t plus phi. And sometimes we can write this as a real part of A e to the I phi, e to the I omega t. And we call this part the complex amplitude, A tilde. Okay, so once we draw the complex amplitude in the complex plane, once we fix the A tilde, classically we know the entire evolution of this system because that sets the initial condition about the initial position and initial momentum. Then that determines the entire dynamics. So the complex amplitude consists of two parts. One is amplitude, the true amplitude. The other is its relative phase. Okay, so now think about classically, this is kind of like specifies everything, while quantum mechanically, this complex amplitude is related to the phase space distribution, which we have, you can think it as a position momentum in some like a scaled units. And quantum mechanically, for example, the cat state correspond to I have a superposition of two complex amplitude to start with, right? You can think I have a harmonic oscillator, and the mass suppose initially both start from plus A and minus A location. So correspond to quantum mechanically, I have wave packets start at the plus A and minus A location. And then at a quarter of the evolution period, then they will both come and meet in the middle. Then there will be interference pattern that you see, and that corresponds to the interference of the cat state. Then half a period, they will come separate again, and that kind of corresponds to the evolution of the cat states, kind of correspond to rotation of the cat in the phase space. Okay, but here all I want to say is classically there's a quantity called amplitude and a complex amplitude. And for classical error correction, we're already using this information for our Wi-Fi and Bluetooth communications. Yes. Here, right. Yeah, this A will consist of the real of A tilde, and this is the imaginary of A tilde. That's right. Yes, X and P span the complex plane for that. Yeah. And so now one thing is in principle, we can just use this oscillator to encode information by saying, well, for example, it starts from initial amplitude A0 or start from minus A0. That can encode one classical bit of information, right? Which in the phase space, that corresponds to, we can have a position, momentum. So I have initially positioning A0 or minus A0. That allows us to encode one classical bit of information. Notice I encode the information in the amplitude. And that's actually very useful because what happened is suppose this oscillator is damping. So it may oscillate and the amplitude will decrease. But if I initially have different amplitude A0 and minus A0, you will find that they will always oscillate in the opposite direction. So even if it's a damping harmonic oscillator, the information I encoded in the amplitude, the magnitude of the amplitude, is actually tells that can encode the information, even though there is a damping in the oscillator. Okay, so that gives us a coding scheme called phase shifted keying. PSK. And this is actually used in our Wi-Fi and Bluetooth. In this phase diagram, you can think that the amplitude is, as time goes on, it will degrade, it will decrease, but the relative, like whether it's amplitude plus or amplitude minus, that information will actually still be preserved if you use a correct reference frame to track what the oscillation is going. Okay, yes. So yes, so maybe let me be a bit more clear. So here I'm plotting is this complex amplitude consists of A0 e to the I phi. And this state corresponds to phi is, so sorry, it's, maybe I said something wrong. This corresponds to phi is 0, and that corresponds to phi is pi. And sorry, I said something completely wrong. The information is not encoded in the amplitude, it's encoded in the phase. Okay, yeah, sorry about that. So if you encode in the phase, you will see that this is phase phi equal to 0, and that's phase phi equal to pi. And doesn't matter how you oscillate, as long as the amplitude don't decay to 0, you will know what the phase is in there. So this, you can say this is a logical 0, and that could be logical 1. And moreover, you can put more blobs here with maybe similar amplitude, but a different phase. And then that you can encode, say, 0, 0, 0, 1, 1, 0, and 1, 1. So you can encode more information as more blobs you may have. But the key is to encode the information in the phase, not in the amplitude. Okay, because amplitude will decrease, but the phase information is still preserved. Yeah. Okay, and this is what called the classical called the phase shifted key. Yes.
Jonathan, is this saying this all bosonic codes sort of have this character, or this is just a specific?
This is a specific classical bosonic codes that we're using. For example, when I communicate with the Wi-Fi or Bluetooth device, I don't know what's attenuation in the channel, but it doesn't matter because the information is stored in the phase.
There could be like a fog. I thought there was some fog.
Yes, yes, yes. I'll come to that because so far I'm talking about classical. Yeah. So everything here you can think it as a coherent states or thermal states. Yeah. But now let's get to actually quantum. Yeah. Yes. Good. So in principle, ideally, if we have good clocks or synchronized, we will know the relative phase. But practically, how they do with Wi-Fi and Bluetooth is they can send two-way packets, encoding information in the relative phase of the two-way packets. Then you don't need the clocks. You just need to make sure the two-wave packets, whether they are the same phase or they're opposite phase. So for example, I send you two harmonic oscillators. You see whether they oscillate in the same way or in the opposite way. Then it avoids the reference frame problem. Okay, yeah. Similar for our optical communication, we also do kind of called time-being encoding that do not need to know like that particular reference frame, so that you just need to measure kind of the relative thing between the two modes. Yeah. Yes.
Some of them don't even refer to these as error correction codes because the error correction is so trivial to them. They're not based on binary. They call modulation scheme.
Yes.
But because quantum error correction for bosonics threw out precisely these types of protections against continuous shifts in phase, we like to think of these classical error correction codes.
Yes. And another example is sometimes people do this polarization encoding, right? They call the dual rail scheme. It's an error correcting codes correcting against erasure error because you encode the photon in two modes, horizontal, vertical polarization. And if you lose a photon, it goes vacuum, which is the third state. And if you don't detect anything on a detector, you actually perform an error detection scheme because you say photon is lost. And you don't record any data, and it just repeats the experiment. So that's actually like many of the things you can think in terms of error correction or detection. It just sometimes people think it's too trivial, they don't even bother to make it to state that way. Yeah. So now let me actually move on to this the background. So one thing I think will be good to briefly touch upon is this Wigner quasi probability distribution. So what the Wigner function does is that suppose you have a bosonic state. Here, I think generally as a density matrix. You can write it as a two-dimensional distribution for position and momentum. And there is an expression tells you how to do that conversion. Okay, I'll just set h bar equal to 1. You basically do this integral associated with the property of a density matrix, which is x minus y and x plus y. And then do the Fourier transform of y, convert y to momentum p, then you'll get a two-dimensional distribution as a function of position and the momentum. So basically, this gives you the conversion, how to go from a density matrix to a two-dimensional quasi-probability distribution. By definition, the entire integral over this distribution will give you value equal to 1. That says it's something property similar to a distribution. However, this function may not be positive definite. So there's some negativity in the Wigner functions that would indicating its unique quantum state. Okay, so here, sometimes that one can even directly measure Wigner functions because there are some ways that you can, this Wigner function can also be proportional to the trace of the parity of a displaced density matrix. So here, the displacement operator is e to the alpha a dagger minus alpha star a. So this is some like a unitary operation that modifies your density matrix. Then you ask how many photons are there? Is it even or odd? And that gives you something proportional to the Wigner function, which is how experimentalists directly measure the Wigner function. Okay, which I'll talk about how to do this parity measurement in a minute, because it's also important for our quantum error correction. Okay, but here, the reason I introduced the Wigner function is because I want to use it to define another property called the Gaussian state. So I'll give more details in the notes, but here the Gaussian states is very easy. It's basically the Wigner function is a Gaussian. Okay, Gaussian states has a Gaussian distribution of this Wigner function. So the examples of the Gaussian states are well known, which includes vacuum or coherent states or squeeze states or even thermal states. Okay, but these states all have the same property, is their Wigner function, it's Gaussian, and also it's non-negative. Okay, so that's why we typically say, these Gaussian states do look like something classical, but one should be careful that the squeeze states, it does contain a quantum ingredient, but it's not explicitly shown in the Wigner probability distribution. Okay, because the squeeze states does give us some quantum enhancement in metrology, which classical states cannot. But at least for our case, we treat them as a Gaussian states because the reason is it's relatively simple to describe it. So suppose you have a two-dimensional distribution, which is Gaussian. You can very easily describe in terms of what's, suppose now you have a two-dimensional distribution, which is Gaussian. You just need to know where the mean is, where the center is, and what are the two principal axes associated with this variance we call the covariance matrix. And if you have, say, like this is a 2D. Now, suppose you have a 2n dimensional modes, which say you have n modes, which is characterized by 2n dimensional phase space. It turns out there is an efficient description for this higher dimensional Gaussian states, because you just need to specify where the center is using 2n numbers, and this covariance matrix using of order n squared numbers. So the Gaussian states can have a very efficient classical description to characterize them. And that's why computationally, it's very convenient to have these Gaussian states. Okay, and now, once we have the Gaussian states, there is also another aspect which we call the Gaussian operations. Let me just do it here. Yes. Mm-hmm. Yeah.
I guess the displacement operator just gives you x plus y and x minus y.
Yes.
But where's minus 1 to the x?
Yeah. So for this part, going from here to there is actually, we can leave it as a homework problem to exploit, because it actually does involve a non-trivial property, which is the integral over the displacement, and the displacement dagger gives the identity. Yeah. So, but this is actually like something, if you look at some earlier papers by Roy Glover and so on in the 60s, it actually gives that justification in there. Yeah. Yes, I think you can think this the y part and combined with the x, kind of that corresponds to the displacement that you impose. And then it becomes just a kind of a binary decision whether it's even or odd. Yeah, but generally after displacement, it's not a parity eigenstate. So there will be some like a weighted average of the parities that you'll get. Yeah, but it can give you negative values because it's negative to some power. the whole thing is alpha. Alpha is essentially x plus IP. Sometimes people divide by square root of 2 and assume this is already dimensionless units in there. Yeah. So now we have these Gaussian states. And so, okay, maybe just bear with me for 2 minutes. The reason I introduce the Gaussian states is I want to point out it is non-trivial to do error correction, to do quantum error correction for bosonic systems. Okay, but the question. Yeah. Okay, just first of all, Gaussian state does not capture all possible states, right? There are states like Fock states, which are not Gaussian states. And but they can give you a complete basis. It's actually overcomplete. If you allow superposition of Gaussian states, you can get non-trivial states. And actually, all the coherent states, when you do the superpositions, you can come up with actually non-unique ways to write down the same states. Okay, it's overcomplete. Okay, but here we're just talking about the state itself. We're not talking about the superposition yet. Okay. So now it's unfortunate that I have to go here, but the Gaussian states, there is another property called the operation, called the Gaussian operations. And the Gaussian operation is basically, it's just a map Gaussian states to Gaussian states. Okay, so now I assume that people already, okay, so this is actually the operation which typically can be achieved by linear and quadratic Hamiltonians for the bosonic modes. And so the examples of Gaussian operations includes beam splitters, phase shifter, and even like a squeezer, and also like a loss channel, which is not a unitary, but it actually preserves the Gaussian nature of a state. Just think about the extreme case of infinite loss, then you go back to the vacuum, right? If you start from a Gaussian state, it actually maps to a Gaussian state, which is vacuum. And also there are also thermal channels. So thermal heating, which also maps it to a Gaussian to a Gaussian. Okay, so now, but one of the, some of the analogy, if you think about the unitary Gaussian operations and the connection to something you might heard about the qubits, is that Gaussian states, in some sense, is a pure coherent. So these unitary Gaussian operations actually something very similar to the Clifford operations for qubits. Okay, and which is actually the reason why Gaussian operations is also, if you consider Gaussian operation on Gaussian states, it's also relatively easy to simulate. Okay, it's because all you need to track is how the center and the variance changes under this Gaussian operation, which is some matrix operations over something or the n or n squared. So you can do it very efficiently. Okay, so now this is actually, maybe let me just, since we're talking about the errors, let's talk about the loss error. I call it a loss channel, or you can think of the loss quantum process. And typically, maybe let me ask, how many people heard about the Lindblad master equations? Okay, impressive. Almost everyone had it. Perfect. Yeah, because that's okay. It's good. We're in the third week, not the first week. Yeah. So we have this Lindblad master equation for the loss channel. So you can think the loss channel, the jump operator, is an annihilation operator acting on rho A dagger minus A dagger A over 2 rho minus rho A dagger A over 2. Okay. This may look kind of a sort of the minimum you can write down for a loss channel. But fortunately, we can actually write analytically what the output of rho is in terms of the initial rho sandwiched by a set of cross operators. But here the important part is, okay, the cross operators, as I mentioned earlier, does have some property associated with loss. So first, for the EL, the subscript L is actually related to how many excitation loss happened to the system. Okay, but that's not everything, because actually there is some like additional loss factor, e to the minus kappa t over 2 times n, where notice that this is the n is also operator that captures, say, like if you have more photons, you will suffer more of this attenuation in terms of the amplitude associated with that state. Okay, and for example, if you don't have photon loss, you will still have this factor, which is related to if you have a coherent state, you don't see any photon loss, actually the amplitude of a coherent state will still decrease. That's associated with the back action of not detecting a photon, which says more likely there's less photon in the system, right? Yeah. Okay, just 1 second. Let me finish this expression. And there is this gamma L is a number. Gamma L is equal to 1 minus e to the minus kappa t to the power L divided by L factorial. So this is the whole expression of this cross operator for the last channel. Okay, maybe 2 questions. Yeah, go first. Okay, yes, so maybe let me maybe read this one, and then later I'll write it bigger. So E subscript L is the square root of gamma subscript L, and e to the superscript minus kappa t over 2 times n hat. And this is a to the power L. Okay, I'll try to write it bigger later on. Yes, Leo. Yeah.
Just to be clear, so the Limblad equation you were in the first line.
Yeah.
Just has one cross up, corresponds to the lowest cross up.
Yes, exactly. You can think it as do like a time perturbation with a small delta t, right? So if you take the t goes to 0, the leading order is L is 0, which is sort of like identity. But it's not exactly identity, because this is still has, if you consider the leading order delta t contribution, there will be some like a small exponential suppression here. But the process associated with 1 photon loss, you will also have some of the term here, which actually give you this Limblad equation. So you can do like a perturbation. Actually, it's yeah, in some sense we can derive this. It's consistent. This is for small time limit. It restores the Limblad equation.
Right. So I'm used to that, but I just I'm wondering if you want to include multi-photon loss as one process.
Yeah. It actually will still follow this equation. The thing is that exactly. So for this system, from like a condensed matter perspective, we always ask, what's the small parameter in the system, right? So there is a small parameter. Which is this gamma L. For example, let's say kappa t is much less than 1. Then the gamma L is essentially kappa t to the power L divided by L factorial. Okay, so suppose I have a system, say have a 10% loss. Then the chance to have a single photon loss is about 10%. Have 2 photon loss is 10% square, 1% and higher. So so that generally will make it smaller. However, that's not the whole story, because we have this A to the L. There's this bosonic enhancement factor. So if I do have a million photons to start with, if I have 10% loss, the most likely photon loss event is about 1 million times 10%. It's about like 100,000, right? So there will be some like maybe Poisson-ish like distribution associated with the loss that you have. Okay. Yeah, but typically when we do the error correcting codes, we have a smaller photon number. So typically the dominant case is no loss, then 1 loss, and 2 loss. However, when you consider like a GKP code and so on, that's a counterintuitive part. Actually, when you go to larger codes, the performance gets even better. And that's a part which we're still trying to understand in a more like analytical way, what that behaves.
So to be clear,
yeah.
The 2 photon loss is non-significant.
Yeah.
Then you would have extra terms in the Limblad?
In the Limblad, no, you will not. Yeah.
A squared, rho A dot.
Good. So the answer is no, but you will get those terms by consider the time integral of this because if you do this like a Dyson kind of integral with a double integral, triple integral, then that corresponds to you have 1 jump, 2 jump, 3 jumps. Then the L case corresponds to the L jump for the Lindblad equations.
Yeah, but all those have the same coefficient.
All those, they will come together,
They'll
contribute that coefficient. Yes, with that particular ratio.
If you have an independent gamma L's, let's say, then they
Yeah, then that would be a different channel. Yes, yes. And it's because like in this setting, the channel is simple enough. It only depends on one dimensionless parameter, which is kappa t.
they come in all with the relation.
That's right. Yeah. But if it's a more complicated channel, then you will need more parameters to specify it. Yeah. Okay. So I think we're still good in time. So maybe here just a few remarks. So first, loss channel, it's a Gaussian channel. Okay, you can verify putting a Gaussian state there after attenuation is still Gaussian. And the operations I talk about over there with this the Gaussian operation, it's also preserve the Gaussianity of the property. So it took people a while to think, okay, can we actually use these Gaussian operations to correct such a loss error? Which is kind of a natural way to think about, because those are the things that are typically available in the lab. And also, if we believe in the qubit from the quantum bits and so on, we actually do error corrections using Clifford operations, right? For this case, unfortunately, there's a no-go theorem, say that you cannot use Gaussian operations to correct loss channels. Okay, so just as a remark about the limitations of Gaussian operations, there are two typical limitations. One is that we know we can efficiently simulate Gaussian operations if it's acting on the Gaussian states. That indicating Gaussian operations alone cannot give you universal quantum computing. That's probably pretty well known. And the other thing is actually the Gaussian operation is also not sufficient for error correction. If we have loss channels, then there is a no-go theorem. Basically says that Gaussian operation cannot correct Gaussian errors. Okay, so that was proven in a paper, which I'll put it in the notes with the references that that's proven in 2009. So basically save people a lot of time, try to do something impossible. But it also gives us a clue, say, if you want to do error correction, we should think about something non-Gaussian. Something not just doing the beam splitter squeezer, we should do something else. Okay, yeah, yes?
It seems true if I have non-Gaussian state.
Okay, excellent point. So now it's about the quantum resource theory, right? So here you can think as a Gaussian operation as the free operations, and the non-Gaussian operations as the non-free operations as the resources. And you can get resources from operations by either unitary or maps or quantum processes, or you can get those resources from those non-Gaussian states, like a magic state injection. And here it's kind of a non-Gaussian state injection that helps you to do something. And a good example is actually, turns out if you have GKP as a non-Gaussian resource, you can use it for universal computing and also use it for error correction. Okay, that's where this company like Xanadu says, just give me a GKP states. I can solve you all the problems. Okay, but it's not trivial to prepare GKP, but there are a lot of progress that people are making on it. Yeah. All right, so now let's actually get to some fun parts, look into some of the error correcting codes that that can correct loss errors. Yes. Yeah, so here, actually the theorem states more generally, it says any Gaussian errors cannot be corrected by Gaussian operations. And the idea of the proof is basically they consider the created quantity kind of called like some entanglement property. And they show that with the Gaussian errors, that property will decrease. And the Gaussian operation cannot increase that quantity. So therefore, they say, okay, the error correction will not correct those errors. Okay, yeah. Oh, if it's a unitary operation, you can, if you know the unitary channel, you can undo it. But if it's a non-unitary channel that somehow increase the entropy, then Gaussian operations cannot restore the information perfectly. Yeah. All right. So yeah, let's look into some of the examples. Examples of Bosonic QEC. So we'll go from small to big. The first, we'll start with the hidden code. And you can look into this paper, PIX, okay, 6, comma. So in the appendix of this paper also derived this channel decomposition as well, in case you're interested. But the hidden code, so when we specify error correcting codes, we need to specify, I would say, at least two things. One is what's the code word, and the other is what is the error it can correct. So for the code word for hidden code is a zero logical, is an equal superposition of Fock state 0 and Fock state 4. And the one logical is just 2 photon Fock states. Okay. Harmonic oscillators, I'm using that notation that I just erased, 0, 1, 2, 3, 4. They just, yeah, they need to be harmonic, which maybe implicitly I will show when I write down the error model. Yeah, it's just an annihilation operator. Yeah, so 0, 2, and 4. So the logical one state is a superposition of those two, and the Fock states 2, that's the logical one.
This is for one harmonic oscillator.
For one harmonic oscillator.
Modes are defined by space, spatial.
That's right. Yeah, you can think that you have different Wigner functions of the 0, 4 states, and there's a Fock states 2 of a single harmonic oscillator. Okay, so here is you can think it as a single mode microwave cavity. It's an oscillator. Yes. There's only single cavity. So that's the surprising part. You can actually just use the redundancy of the oscillator itself to do the error correction. So there is just one oscillator.
Like, suppose I want to do 2 qubits. There will be 2 resonators.
Oh yeah, if I want to do 2 qubits, I have to have 2 resonators, and I have n qubits, I have n resonators. Yeah. So it's a one oscillator encode 1 qubit. Of course, there are many ways to encode, but this particular choice, it can correct single photon loss error. Okay, but let me write down the correctable error. Just identity and annihilation operator. Okay, notice that there is a slight difference between the correctable error I've written here versus the cross operators over here, because the identity is probably like almost, well, it's even the identity not the same, because here I put L equal to 0, I still suffer this kind of like a back action with no loss. But if we say like, this is much easier to compute, and later we can translate into that part, okay, to compute the true performance of the codes. Yeah. Okay, so first, are there any questions about the setting of the code word and the error model? Yes.
How should I understand physically that we wouldn't need to worry about, for example, photon gain?
And physically, we need to worry about it, especially if it's microwave systems. But here, I just want to keep it simple with the smallest code that can correct loss error. But later I can talk about with the generalization, you can correct photon gain as well. Yeah. But here you cannot distinguish between loss and well, you will get confused whether you have a loss and a gain, right? Yeah. Yes. Sorry, could you say that again? Yeah.
What does it mean for there to be an identity error?
So identity, I just want to, how to say, the error, what's relevant is that I want to define an error space. So any combinations of the error space, I think this code can handle it. Yeah, so those are the kind of bases of error space. Yeah, Leo. Yeah.
So if you have a fully harmonic oscillator, how do you, I thought the whole point is that it's very difficult to address something that's harmonic because, you know, you send it, you drive it with some microwave.
Yes. Yes. Yeah.
So then how do you get?
Yeah. Oh, well, are you saying if I have harmonic oscillator stuff from vacuum, how do I even prepare such a state?
Exactly.
Right? Yes.
Is there some enough harmonicity?
Yeah. So one way you can think of it is you can switch on and off the harmonic coupling. You can encode it and you switch it off, and maybe let it send through optical channel or microwave cavity, let it stay there, and then later you switch on the harmonicity using another transmon to, for example, measure parity and so on. Yeah, so there are some switchable parts because, as you said, if this becomes aharmonic, then I should not write the error as an annihilation operator because this will be frequency dependent, right? Depends on the level dependent, so it's a more complicated error for here. Yeah. Mm-hmm.
You're like 0 and 4 states because you're right.
Yeah.
I think that somehow you're rotating frame because, you know, they oscillate with different.
Good. Yes. So there should be a reference frame to be defined because these are not the eigenstates of the Hamiltonian, right? But actually, I would implicitly assume we go to the rotating frame of that Hamiltonian. Or you can think that there is a local oscillator that tracks the phase, relative phase between 0 and 4. Yeah. Exactly. Exactly. You need to sort of like track the relative phase between them. Yeah, either in a rotating frame or in a physical, in a lab frame. Yeah. Yes.
For quantum compression, do I need to worry about like this?
Yeah. So here, maybe it's a good time to, we can connect to what Victor would just mentioned at the end of the last lecture about this error correction condition, right? And here, but just maybe 1 minute, let me just point out how this correct errors, then we can take that perspective to understand that this particular code. Okay, so now suppose I have a photon loss error. What happened is I apply an annihilation operator to this logical 0 state. What do I get is when I apply annihilation to vacuum, it disappears. Annihilation operator on 4 photon state, I bring out a square root of 4 factor. Divide by the square root of 2, I get square root of 2 acting with a 3 photon Fock state. Now for this 1 photon state, this 1 logical state, I apply annihilation operator, I get the square root of 2 with 1 photon. So 2 features. One is these have the same coefficient, which in terms of normalization, that indicating I have a photon loss, which is equal likely happen for logical 0, logical 1. If you trace it back, it's because both logical 0, logical 1, they have average 2 photons. Okay, and it turns out these are orthogonal, so any linear superposition or mixture of logical 0, logical 1, they have 2 photons, which means based on the likelihood of photon loss to the leading order, you cannot differentiate between these states. And so these states are equal likely to have photon loss to go to this space. The second property is also obvious, is that this is an even number photon. When you have 1 photon loss, it becomes odd photons. So if you could measure photon number parity, you can project out these subspace. And then, because 3 and 1 are orthogonal, and the logical 0, logical 1 are also orthogonal, you can design a unitary to restore to the original logical space. Okay, So with those two arguments, you can say that I can perform error correction. So maybe to make the first argument a bit more clear is that I can have this logical 0, say C0 plus C1 logical 1. If I undergo a photon loss, what happened is it becomes a square root of 2 times C0, 3 photon states, plus C1, 1 photon states. And this is still orthogonal, and also this still maintains the same proportionality of the coefficient as the original code word. And my unitary recovery can actually restore it to the original state. Okay, but whether or not I should apply unitary recovery is informed by a parity measurement, whether or not the photon is in the logical space, even space, or the error space with odd number of photons. So the procedure will be first, after some time, you measure parity. Is it even or odd? If it's even, which means there's no photon loss. If it's odd, which means there's a single photon loss, then what you should do is to do this recovery to restore to the original space. And such unitaries always exist. It maps from orthogonal basis to another orthogonal basis. And the choice is not unique. You may choose whatever you like to do the recovery. And moreover, there is a subtlety. If there's no photon loss, then one should be extra careful, because there is a back action for the true no photon loss errors. Okay, but I'll come back to that later. Before, are there any questions about this ideal case with ideal identity and the photon loss annihilation error?
So this is the reason for your choice of 0.2.
Yes.
You don't change the 0, C0 and C1. You leave the code space.
Exactly. Exactly. So I choose equal superposition of 0 and 4 so that these coefficients are exactly the same to maintain the original superposition. Or equivalently, as I think probably Victor will also talk about, from the environmental perspective, there's no way for the environment to get information based on the single photon loss, because it's equal likely there is a single photon loss. Yeah. Yeah. Sorry, is that a question or comment? Okay, thanks. Yeah. Yes, if you have a dagger, you'll spoil it, but but there we have a way to resolve it. So, but just maybe let me connect it to what Victor was talking about, the error correction matrix, quantum error correction criteria. So, this Knill-Laflamme condition, which Victor given, was suppose there's a projection to the logical space. You can define the projection to be the 0 logical plus 1 logical, right? That's the projection operator. And the error correction condition is a projection, and with the error EI, I think Victor called it NI, and EI dagger EJ with the projection. This should be proportional to the projection itself, right? The proportionality indicating there should not be any bias towards one particular state over the other. And also like this error correction, if I, instead of writing the proportionality constant, I can say this is equal to something that depends on the index choice of I and j. I will call it the alpha ij as kind of like tracking these coefficients. So now one way you can verify that for this set of errors with no loss or 1 loss, identity and A, this error correcting code fulfills this condition. And to do it, to make life easier, instead of writing these as operators, I can project it into different code words, say like I'll write the psi k as a code word, psi l as another code word, could be logical 0, logical 1 in here. And the projection acting on these psi k, psi l is trivial because these are already in the code space. So I will write it as a psi k ei dagger, ej dagger, or ej. So sandwich this expression by psi k, psi l from both sides. This will be equal to alpha ij. And if psi k, psi l, they are already in the basis, then this will be the delta KL. Okay, for like a 5K phi L as a logical basis. Okay, so now what we can do is basically to verify that this condition is satisfied. So this is something to be verified. And you can show that once this condition is satisfied, you can also go back to the original error correction condition. They are equivalent. And the reason I'm going this is this just shows the numbers are equal rather than operators are equal. Okay, yeah. 10 minutes? Okay, good. Yeah. Mm-hmm.
I must not be following that. Seems like I could go K and L maybe not equal, but then J flips L into something. And
yes.
I flips
yes.
that K and L.
Exactly. So it's important that this is KL being delta function so that I don't mix between different logical basis states. Okay. And well, this is equivalent to what Victor said about the error correction condition. It's a condition. And generally, the left-hand side is a four tensor with 4 indices. And the right-hand side say the 4 tensor should be decomposed as the product of 2 tensors, and one of the 2 tensor is a delta function.
If it's not true,
if it's not true, then you cannot perfectly correct that error. So this is actually a necessary sufficient condition for error correction. And let's actually just verify that this is the case for our this Kitten code. So EI dagger EJ, and I'll put this as a phi K, and the other side as phi L. So basically, the phi K can be 0 logical or 1 logical. The phi L can be 0 logical and 1 logical. Okay, so once I put in these here, I can put the I and J in there. Now, for example, if they're both, let's do the 1 logical is easier because it's Fock states. I can just look at the numbers. It's a 2, 2. So if EI, EJ are both identity, then the sandwiching between the logical states, it will be equal to 1. If EI, EJ are both like the A and A dagger, and then that will becomes the A dagger A is the average photon number. For the 2 photon states, it will give you 2. And the off-diagonal terms will be 0. So you can verify that this lower block part, it's the matrix, which is the Hermitian matrix, 1, 2 in the diagonal. You can verify for the 0 state, it's the same property. Okay, for the off-diagonal part with the 0 and 1, this is everything is 0. And this part, everything is 0. So notice that the structure that this being 0 and this being identical is consistent with this delta KL condition. And this exact form of this matrix that determines what this alpha IJ matrix is. Okay, so this kind of give you the verification that the error correction condition is satisfied. Okay, but this is more intuitively. Think about you can construct a channel, and this is more formally you can prove you can correct up to single photon loss errors. Okay, so and basically for any logical code word with the selected errors, you can make this table and show exhaustively that this is actually fulfilled error correction condition. And I think that later on, now it's actually a question about for realistic errors, which is even for E0, it's not exactly identity. There is this e to the minus n component. Then this is actually will cause a little bit deviation from this exact form. And that means that we're not going to even perfectly correct the error. And that's related to some approximated error correction and for real physical systems. Or put another way, is even for our qubits, even for Google's like a surface code device, there's no way to do a perfect error correction because there's always some infinitely small chance that all the qubits kind of goes wrong, right? And so it's always about approximated error correction, but the question is to what a good approximation we can do error correction. Now for, and here is probably the punchline for this case, for the Kitten code, that you can correct errors to the order, originally it's kappa t, which is associated with a single photon loss rate. Now it's being suppressed to kappa T square. And one way to see that is that if you have a 2 photon loss, which happens at the kappa T square probability, then the logical 0, there's some chance it could be mapped to a 2 photon Fock state. Then there is no way you can distinguish between logical 0 and logical 1. Okay, and so maybe just a few more remarks about this code. So first, we implicitly assume we can measure photon number parity. And how to do that? Okay, how to measure parity. And different from photon counting, we cannot count the photons, okay? Because once you count the photon, it collapses everything to a Fock state. We just want to get one classical bit of information of parity. And we need to do it in some like a non-destructive way, okay? And now the second comment is actually related to the realistic error of this back action. The back action is related to even for no photon loss case. Let me write as the E tilde 0, which is associated with the cross operator that I've written here. When L is 0, then this operator is essentially equal to e to the minus kappa T over 2 n hat. And to the first order, 0th order approximation, this is identity operation if you treat kappa T as a small parameter. But even to the first order, there is already a deviation. And we actually need to treat that carefully in order to be able to fully correct that error. Okay, so let me just clarify this, and I think probably that will be the end of today's lecture. Okay. So if we look into this 0 plus 4 states, undergo this E0 error, what happened is that suppose initially it's 1 over root 2, 0 plus 4. Now it becomes 1 over root 2, 0 plus e to the minus 2 kappa T times 4. Okay, notice it's no longer an equal superposition of those states. What you need to do is, if you detect its even parity, you need to actually perform another recovery to rotate this state to be something proportional to 0 plus 4. Because if you don't do that correction, then the population in the fourth state will keep decreasing, and then you will actually end up in the vacuum with order of time kappa T, kappa inverse. But the claim for this code is that it should be able to store the information for the order 1 over kappa square, right? Kind of that scale. So therefore, that we need to actually suppress, make sure that we restore to the code word so that it will maintain the capability to correct errors. Or another way is that if we don't correct, the average photon number for this state will be less than 2. So if we don't do anything, the next round, the photon loss will actually cause an additional bias between the different logical 0 and logical 1 state. So this is actually something extra that one need to do to correct the back action errors. Okay, and maybe one last thing is you can generalize to binomial code, and sometimes also called the rotation symmetric code. And that can correct multiple loss errors or combinations of loss and heating errors. So, but the key idea is essentially very similar to this one. You just put more photons in there and introduce more photon number spacing, and you can correct those errors. So maybe in the next lecture, I'll probably briefly talk about this and then talk about the CAD codes and talk about how to do the photon number parity measurement non-destructively. Okay, yeah, I think that's all for today. Yeah, thanks for the attention. Yeah. Oh, yeah. Oh, sorry. Okay, that's for next lecture. Next lecture, yeah. Yeah. Oh, the question is how to measure the parity, and I will explain it in the next lecture.